going to introduce you to deep learning for developers and a little bit about myself. I work on the MXNet team in Amazon AI. So we focus on developing deep learning systems for developers and scientists. So as for me, I mainly work on the deep learning framework called Apache MXNet. So it's an open source project. It's incubated on the Apache. And yeah, I think that's pretty much it. So let's look at today's agenda. So I'm going to talk about deep learning is a big deal, why it's important and why you should care about it. Then I'm going to go through a brief introduction to what is deep learning. Next, I'm going to show you some code on how to use the frameworks to build neural networks. And lastly, we'll show you a hands-on example on how to train and inference. Before we go into details, I'd like to understand today's audience. Can I have a show of a hand if you have used any of the deep learning frameworks called like Keras, TensorFlow, PyTorch? Okay, I think yeah. That's pretty good. So I made since only a few of you have used that, I think I'll go a little bit slow on the introduction part. Let's get into it. So deep learning is a big deal. Let me start with quoting Andrew Ng, who is a pioneer in this field. Deep learning is a superpower. It can achieve a lot of things, from synthesizing novel arts to new machine translation. And I don't know what that is if it's isn't a superpower. Next. So a little bit about histories. So I believe many of you have often heard the terms artificial intelligence, machine learning, and deep learning. So here it is. So first comes artificial intelligence. It's a term coined in the 50s by Alan Turing, which changed the question from can machine think to can machine do what we want. It's like can machine imitate us humans. It's a very broad topic. It covers from philosophy to science. Next, in the 80s, there comes the machine learning concept, and it's widely adopted in the 90s and early 2000s. It basically changed the paradigm of classic programming. So in classic programming, we just basically code rules. There's input data. We apply the rules. There's expected output. However, in machine learning, we have algorithms that we just pass them inputs and we pass them label data, which is the expected output. They will figure out the rule themselves. So there are a few machine learning techniques. For example, logistic regression, support vector machines, and decision trees. So that you might be familiar of. Then later, besides on that, there comes deep learning. Deep learning is just one of the topic of the machine learning techniques. It's also referred to as neural networks or artificial neural nets. So it became powerful most recently, mainly because there are more computing resources we can leverage. There are more powerful CPU and GPUs. And nowadays, you may have heard of there are TPUs from Google, which specialized in neural machine training. So deep learning is a big deal, and I'm going to demonstrate, show you how it's going to impact our lives. Take Amazon, for example. So when you use Amazon to shop and to watch videos, to listen to music, there's personalized recommendation systems. They are based on deep learning algorithms. In Amazon's warehouse, there are robots that help to ship and pack packages. So it applies in logistics. Of course, there's the famous Alexa. So your voice command assistant is powered by deep learning algorithms. And last but not least, there's autonomous vehicles. And in Amazon, we try to use drones to deliver the packages. So another thing about why deep learning is important is that sometimes it can do better than humans. For example, take the example of this classical image classification problem. You have an image. Now you have a set of predefined classes. You want to predict which class this image belongs to. For example, I want to predict what type of cat is this. So we have compared different neural network models to actual human performance. Right now, these models are actually outperforming humans. You can see here in both color and grayscale images, these models are getting better and better, starting with the oldest AlexNet, then comes from the GoogleNet, and then VGG16. So I think besides that, just to make you feel better, I think humans do much more better than machines in in aspect to generalization problems. So here's a little, go into the technical details. Here's a little demo on the NVIDIA's DriveWorks platform on autonomous vehicles. This is not possible prior to the existence of deep learning. So as you can see, this is a live stream from one of the vehicles they're testing, and they have bounding boxes on the vehicles. On the cross traffic, you will see it's white boxes. On the same traffic, you will see it's red boxes. In addition to that, it can also recognize lanes to help you keep in the lane on the highway. And this, I think this is an example of LiDAR. So it helps to segment what is the road and where's the buildings and cars. And you can even see it can recognize pedestrians. So it's waiting pedestrians to cross the street. So all of this is not possible prior to deep learning. I think it's simply because there's not enough computational power, and now we have that, and we have algorithms. To combine them, we can achieve autonomous vehicle and self-driving. So let's get into a bit of the technical details. It will be a very brief introduction on some topics on deep learning. Let's start with artificial neurons. So it's inspired by the brain's neurons. Our humans, we have 100 billion of them, and 1 quadrillion of synapses to connect those neurons. One example is that in our eyes, we have thousands of neurons. Some neurons are sensitive to green color, or some are sensitive to shapes. So we try to imitate that in computer science. So artificial neurons is simply a construct that, so given input of x to xn, I want to apply a set of trained weights, which represented here is from W1 to Wn. And then I just sum them together and then pass them to a activation function theta. And then it will produce a result called y. In mathematic form, you will see it's just we apply the weights on x and then sum them and then activation to get y. So this is to simulate our neurons. For example, if green light is shed in one of the neurons in our eyes, and it stimulate according to the weight, it stimulates this neuron, and so it's activated. Yeah.
How are the weights assigned?
How are the weights what?
Assigned.
So in our humans, our neurons are evolved. So by generation. So some of our neurons are developed to be sensitive to certain features. Some of our neurons are developed to be sensitive to some other features. Same thing happens to artificial neurons. So we can, let's say, initially I just randomize the weights to be all zeros. And during the learning process, I learned the weights. So some of the neurons will be, some of the weights will learn to be sensitive to some colors, similar to humans. So as for how are the weights learned, we'll talk about it a bit later. So as you can see on the graph here, this is a typical neural network. On the left-hand side, there is your input layer, and on the rightmost side is your output layer. In the middle, there's it's called hidden layers, and there are different stacks of layers and different types of hidden layers. We'll first talk about fully connected layer. So yeah, networks are comprised of stacks of layers. And so the definition of fully connected layer is each neuron is fully connected to the previous layer and to the next. So each of these neuron will have the weights associated with them, I just talked about, and it will be learned during training. Another layer is called convolution layer. It's very used for computer vision problems. So in computer vision, think of, for example, an image. Computers see images as pixel values. So given an image in the computer, it only see what's the value on the each pixel. You can see on the example here. And how does convolution layer work? We introduced the concept of kernels, which is there can be many kernels in one convolutional layer, and we slide the kernel over the input to produce the output. So this sliding process is we call it convolve. So that's why it's called convolutional layer. And so each kernel can be specialized or trained to capture certain features. As we can see, this is very lower level output of the kernel, so it won't be. It's not very clear of what feature is it capturing. But as we stack convolutional layers together, it can abstract hierarchical information from the image. So take another deeper look. Let's say we stack several convolutional layers together. In the first layer, the kernels in the first layer will mainly be subtracting features like edges. So whether it's a straight line, it's a cornered line, so that's the information captured. On the second layer, the kernels will mainly focus on capturing curves, like circles, eyes, and so on. So we stack more layers, we can abstract more hierarchical information. And in the last layer, it will be classes. So we can tell whether an image is a dog or a cat, or even what kind of dog this is. So besides computer vision, there are other machine learning problems. And we use other types of neural network layers. So in some problems, predicting a given point in time depends on the input context from earlier time. The example is text translation. So, or natural language understanding. Each word under different contexts may have different meanings. So how do we understand that? We use a layer called recurrent neural networks. So you can basically intuitively understand it as it remembers past using loops. So let's say the same, given an input X, I pass it to an activation function. It gives me an output Y. Now I loop for the next X. I put it as an input, but also I put my previous Y as the input at the same time. In this way, I will have information of the previous inputs. So to help you understanding more clearly, we can unroll our RNN layer. So instead of executing loops, I can execute it in a sequence. Here you will see x0 as input, and then h0 is a output. We call it hidden states. Now for the next input, I use x1 and h0. Then for the next one, I use x2 and h1. In this way, it has information from the past, and this is really a simple example of RNN. And we have more complicated ways like LSTM, which can allow you to remember, forget, pay attention to, or ignore things. So besides RNN, I think another type of neural network architecture are called transformers, which are getting more and more popular. You might have heard of the models BERT from Google or GPT-2 from OpenAI. Those are the state-of-the-art models on NLP problems now, and they're using transformer architectures. So I would think in the future, transformer architecture will replace RNN layers. Now, you've learned that neural networks consist of multiple layers. They're combined together. And they're applied nonlinear activation functions. And they can learn hierarchical features from data. And it's a scalable architecture, so it can be very large, and it's very computational intensive. So I've talked about the architecture of neural networks and how the neurons and weights are activated. But how do we do training? How do we learn the weights for each neurons? A typical machine learning, a typical neural network training process consists of the forward pass and the backward pass. So in the forward pass, I have input data. I feed it into the network. I get an output. Now I compare the output to the true label, which is the correct answer. And then I can calculate a loss function. So it describes how right or how wrong I am. So the more correct, the loss is lower. And our goal is to make the output of our neural net try to be the same as the correct answer. So our goal is to reduce the loss. But how do we reduce the loss? There comes the technique called backpropagation. So once we have the loss, I want to change my weight or learn my weight to make the output as close to truth as possible. I can compute the gradient of the loss with respect to the weight, and I can compute those gradients for each layer using the chain rule. And once I have the gradient, I know how I want to change my weight. Basically, where it's telling me whether I should increase certain weight or decrease certain weight. Now, once I know that, I can just update the weights. And then what else? Let's do it again. So usually, deep learning requires a lot of training data. I have to loop through them over and over again. And so I'll keep calculating gradients and updating weights until one time, my gradients will be 0, which means ideally my gradient will be 0, which means there's nothing to optimize or there's nothing to update. That means you have learned everything from your training data. So that finished the training. Okay, now I'll try to show you how to code neural networks. So as you can see, the neural network architecture can be very complicated, and calculating gradients and weights, updating weights can be very troublesome because there's thousands of neurons and can be billions of parameters. So we created deep learning frameworks to help you do that more easily. There are many different frameworks. You may be familiar with TensorFlow, PyTorch, Keras, or MXNet. They are all available on AWS. You can choose whichever you want. I'm on the MXNet team, so I will use MXNet, for example. So if you have a Mac, you can easily do pip install MXNet to use it. It's a Python package. And if you have a GPU-enabled machine, so there's some setup to do. You have to install the, for example, NVIDIA drivers, or you have to install some CUDA libraries from NVIDIA guys to speed up the calculation. However, at AWS, we have did it for you. So I think I would recommend two choices. First is the Amazon SageMaker. It's basically a hosted notebook service, and with a instance, AWS instance in the background. You can choose what type of instance you want, a powerful GPU for training or a powerful CPU for inference. And you can just launch your notebook in the browser, and then it has everything configured for you. You can just take an example and start training. On the other hand, if you want some flexibility, you can always launch your own AWS EC2 instance. We have our deep learning AMI for you. So if you just launch that, all the frameworks are pre-installed in this instance, and they're perfectly separated using virtual environments, so they don't affect each other. Now, let's see some example. So we want to build a LeoNet, solution for digit classification. So I have a digit, I want to handwritten digit. I want to recognize which one was it. This is like the hello world in deep learning world. So typical LeoNet consists of convolutional layers, max pooling, and then fully connected layers. We have talked about convolutional layers and fully connected layers. So what does max pooling do? Here you can imagine it is just getting the output of the convolutional layer, and it's downsampling it. It will help to make your model more robust. So what does it mean robust? I think take an example of image classification. I want to tell the difference between dogs and cats. So, and I train a model. It can be, the model can predict it's a dog or cat based on the background. For example, if he see grass in the background, he may think it's a dog. If he see couch or indoor background, he may think it's a cat. But this is not very reliable. This is not a good feature we want the model to learn. So we use various techniques to make our model more robust, so it can pick up good features. For example, the shape of the nose or the shape of the ear. So max pooling is just one of them. So let's go to this example. So here's a live example. If I just write a digit here, 8. So as you can see, this is visualizing what each layer is doing. So there's the convolutional layer is abstracting some information. There's the max downsampling, which is the max pooling I just talked about. There's a second convolutional layers, additional abstracted some information. Then there's downsampling, and then we just flatten them. Basically, this is to reshape multi-dimensional output to single-dimensional, and then we connect the fully connected layer we just talked about, and then finally it predicts the output. So you will see in each layer, some neurons are activated because it captured certain features, and some are not. And then we start layer by layer, and then finally the last layer, I think it predict wrong for 6. Let's try another one. So yeah, for 7, you can see some of these kernels are detecting edges or corners. That's why it was successfully to capture those features and predict this as a 7. Yeah, let's try another one. 9. Okay. So maybe this, maybe my handwriting is not so good. Yeah, so this is 9. Here we go. Let's continue. So now let's build a network just like that using MXNet. So we are using the Python interface from MXNet, and this is called Gluon. So MXNet is a deep learning framework, and it has different interfaces. For training, I would recommend just using Gluon. Gluon is a high-level interface to help you easily build and train models. It's very similar to PyTorch. So let's say you want to build a model as just initialize a sequential class. So which means sequential means I want to stack layers sequentially together. Now I just add the layers. Now, as you can see, convolutional layers, max pooling, convolutional, max pooling, flatten, and then dense. Dense is the same as fully connected. Okay, you might be wondering what are these parameters here. These are called hyperparameters. I can change them to change the network. For example, channel, which means how many kernels do you want for this layer. Generally, you start with a small number and then increase it gradually. And then kernel size is how large is the kernel I want to convolve on the input. And then you have activation, I just talked about, and ReLU is just one of the activation functions. Okay, we have defined our model now. Let's go to the training process. I've talked about during the training, we want to iterate over the data. So let's say I have 10,000 images. I will just loop over them. So epoch means for each epoch, I loop over all those 10,000 images. Usually I will just do that for many times, like for example 10, I'll do 10 epochs. So I'll loop over those all images 10 times. Okay, so first we define our loss function. We talk about it is measuring how you predict to the true, how you predict compared to the true label. And the trainer is, we just initialize a Gluon trainer and specify I want to use a SGD optimizer with the learning weight 0.1. So SGD is a type of optimizer, scholastic gradient descent. It basically helps you to optimize your weights and move towards the best value. And the learning weight is describe how aggressive you should move on each weight update. Okay, then now in the training process, it's a simple for loop. You just write like this, and then from your training data, you have input X and your true label Y. And once you pass it to the net, you have your prediction called Y hat. Then you can simply pass Y hat and Y to calculate the loss. And then based on the loss, you will do backward. So in this backward, yes?
Should you just randomize the weight distribution?
Yes, so that's done before before the training process. Yeah, so before this for loop, you can just initialize your weight. It can be called by net initialize, and you can pass different method of initialization. Yeah, I think now when you go backward, it just helps you to calculate the gradient and apply the weight update. It automatically does that for you. Next, you just have to do that again. So I just talked about there are 10,000 images. I don't want to do that in one time. So we do that usually batch by batch. So, let's say usually I do it 32 by 32 on CPU. So each time I will just calculate this for 32 images. Okay, now we have trainer model. So there are so many models out there, and there's so many papers published. We have provided you pre-trained models that's available in our Gluon Model Zoo. So you don't have to do the training because it takes a very long time and it's very troublesome. You can just use it. So how can you use a pre-trained model? There are several ways. First, you can just use it as is. If you have an image classification problem, you can maybe just use a pre-trained ResNet, which is a very good model for that. And you can, another use case is you can fine-tune with your own data. Let's say you have only a few thousand images. You cannot train a good model because the data is too small. You can use a pre-trained model and fine-tune on a data set. So I continue to update the model's weight so it best perform on your own data. Another use case is you can use it for transfer learning. So transfer learning is I use my pre-trained model as a feature extractor. So I just extract the features and then I can use those features for some other tasks. So let me demonstrate a bit how you can use Gluon, use it. In Gluon, you can simply import our model zoo, which is a collection of pre-trained models. And now I can just initialize a ResNet 18 here and specify it as pre-trained. Then suppose I have some input data, I just pass it to the model and get an output. And then finally, I want to predict the classes of this X. I use a softmax and to convert the output to probabilities of each class. And then I just take the first top 5 probabilities of the classes it predicts. Okay, now you have trainer model. You maybe get a or you have a pre-trained model now. Usually the next step, you want to deploy it for inference for your service. There are many ways you can deploy your models. There's Amazon SageMaker. You can deploy it with one click. You only have to train your model once, and then you can inference on different devices. There's, if you use Internet of Things, there's AWS Greengrass. And you can always use AWS EC2. That's the most flexible one, and to build a service. And then there's container service for you. And then you can build it on mobile or edge devices, or you can have your own solution. So let's show you in the terms of MXNet. Let me show you some example. So let's say you have a trained model, you want to deploy it, and your service is using Java. We have a various language bindings for you: Java, C++, and Scala. You can integrate this with your existing service, or even, for example, you have Spark in your data pipeline. You can use our Scala binding for MXNet to do distributed inference. And if you have a service written in Java, as here, you can write your Java code according to our Java APIs. For example, here, I'm just defining a context, which is the device I'm going to run inference on. It can be CPU or GPU. And then I create an input descriptor, which describe our input shape. And now I have constructed a predictor. And then to specify the models I just trained. Now, after that, I can load my images and do some pre-processing. Usually you want to put it in the same size as you train. Now you can just do predict and you'll get the results. So I think that's pretty much it on the whole process. And I talk about how Amazon uses it in all of its services. And beyond that, you can also use that in healthcare, finance, cybersecurity, or even robotics. And here are some good resources to get started with deep learning. So if you want to get started with MXNet, I would suggest you start with Gluon. There's a Gluon crash course, which is only 60 minutes to go through. And there's also SageMaker tutorials to help you. You don't have to worry about all the setup. You can just run your code there. All right, now let's see some real code. I'm going to take over this screen. So in this example, we are trying to do a facial emotion recognition. First, we just import libraries we will be using. We'll be using NumPy, MXNet, and different components from MXNet. Okay, so this is how your data like. You have grayscale images, and each of them is one of the emotions. This is maybe a surprise, or I don't know. The first step you're gonna do is to process your data, to clean up your data. Yeah. Okay. So the foundation of a good neural network model is clean data, or good data and good label. Now I clean up my data and labels. Now there are 8 emotions: neutral, happy, surprise, sadness, anger, disgust, fear, and contempt. And I do some pre-processing. It's called image augmentations. So it can consist of shift image, flip image, or rotate some angles and normalize the pixels. So image augmentation is a very common technique in computer vision problems. It helps you to just randomize your data, to introduce some randomness in it, because for a model, each small change you introduce, it considered as a new image. And in this, it will help you to make your model more robust. Okay, so we have the labels. Here. We map each integer to one of the classes we have, and I think I need to refresh. So let's take a look at our training images. We have 25,000 training images, and the shape is 64 by 64. And the one here means there's grayscale images. And our labels, we have the same number as training images, and 8 means there are 8 labels for the label. Okay, here is one of the example of training image. It's more like a surprise. Besides training images, we also have test and validation. So we usually separate our training data into 3 sets: training, validation, and test. Training, of course, is just for training your neural net. Validation is, for example, at the end, it's never used for training, and it's used to predict your output at end of each epoch. It can evaluate how your training is going. You can adjust some of the hyperparameters to increase the validation performance. And for the test data set is finally when you're done with the training, you want to test it on an untouched data to see how it performs. So we're done with the data preparation part. Let's go to the model training part. So this is a slightly more complicated model than we just talked about. It has, as you can see, it has more convolutional layers. each convolution layer have more kernels. And then this green and orange color layer is the max pooling and dropout. I've talked about it. These two layers will help you to make your model more robust, to help you pick up good features from the input. This is how you construct the model we just see. So pretty similar to that, you create a sequential model, and then you stack a bunch of layers, count to the max pooling and dropout, and then you specify the hyperparameters we just talked about. And then in the last, you flatten them and then add fully connected layer at the end. And then in Gluon, we have something special called hybridize. So it can help you speed up your training. Usually in deep learning frameworks, there are two ways of doing building models. It can be either imperative style or symbolic style. And Gluon actually has both. So you can start with imperative style of programming, which gave you flexibility, and you can call hybridize to use symbolic style, which is static computational graph, which can be faster for most of the cases. You can just Google it for more information. Okay, here is before the training start, we have to initialize the parameters, which are the weights we just talked about. So you have to collect them, initialize them, and pass an initializer. Now let's visualize the model we just built. So we can plot it. So basically it's the same as we see in the above graph, from input to convolution, and then to activation, and then max pooling, dropout, and then dense, which is fully connected. Okay, so this part is the same. For classification problem, we use softmax coarse entropy loss, and then we initialize the trainer, specify our optimizer, learning rate, and momentum. Besides that, we have to define our evaluation function, which is at the end of each epoch and at the end of training, we want to evaluate our model based on the validation data and the test data we just see. Okay, to help you prepare the data, Gluon has a set of API called data loaders. You can simply just specify where is your training data path and how other transforms you want, image augmentations. We just talked about you want what augmentation you want to apply on images, and then it will do it for you. Okay, here is the training part. So I want to iterate over the whole data set 25 times, and it's basically the same. It's a for loop. You load the data from your data loader, and then you pass the data into your net to get output, and then calculate your loss, do back propagation on your loss, and then step on the next batch. So that's pretty much it. During the process, you can also print what's your current loss and accuracy. Here you can see the output of each epoch. You can see the loss will go down, and then the training accuracy will increase. And the validation accuracy is slightly below training accuracy, but it also increased to around 80%. Now, once the training is done, we evaluate the model on test data. And you can see here, it also has around 0.8 accuracy on the test data. So it's pretty good. Here, this part, we're just using matplot to plot some of the metrics we just used. So this is loss. As you can see, as the epoch increased, the loss will decrease, and the accuracy will increase. Now let's test our model. We just randomly specify some index from the training data. This is the image, and this is the actual emotion from the label. It says happiness. Now let's predict it. So you just pass your input to our net, and then to see which, and then you can use print it out from the predicted classes, you will see happiness. So we have finished the training part. Now let's try to deploy it for inference. So for inference, MXNet has a package called MXNet Model Server. Basically, you just provide the model you just trained, and it can host it for you. And you have an endpoint to query your result. Basically, you can just pass image and make a query to your host, and it will return the predictions. First, before that, we need to save our model. You can simply use mnet then .export. So this will save two files. First is a symbol.json file. This JSON file describes how your model architecture is. And the other one is params, which are the weights we just trained. We just serialize it into a param file. Here's the part you just pip install MXNet model server, and we used OpenCV and some other libraries for visualization. Okay. We have hosted this model for you. You can directly access them. Okay. Besides those two files, another thing you need to prepare is called a synset. So synset is just mapping your, yes?
Yeah, can you go back? Where does the softmax cross entropy come from?
Yeah?
Yeah.
Okay, this is, sorry? This is from MXNet Gluon. It defines your loss is computed, how your loss is computed. Usually, it comes. There are two concepts in this. So one is softmax, one is cross entropy loss. So softmax is basically converting your output to probabilities, and then cross entropy is a way of calculating loss. It's a log loss. So once you have the predicted labels and it compared to true labels using log, basically it's just a mathematical function tells you how well you predicted. So let's go back to the model server part. Okay, so yeah, this synset is just for easy printing, converting your digital labels to actual meaning of the class. So you have to write a small web service, maybe call it a FER services. This will basically you just have to define to extend MXNet-based service and define how you want to pre-process your request and post-process it. Now you want to launch your service. Before that, you have to pack your trained model, synset, and everything into your symbol archive. You can use MXNet model export and specify your model name, your service file path, and your model path. And then after that, you can just spin up a process which listen to input queries. You can ping your service. And here we can test on this image. This is actually Hagai, and he's a hacker guy. So let's test his face. You can post to the model server and to make a prediction on the data. And you will see here, so the probability, highest probability is happiness with like 0.5, so the model is not so sure, and with 0.38 neutral. I think that's pretty much it. And then after that, you can just terminate your service. So I think yeah, with that, this finished my presentation today. Thank you.